Hello everyone, welcome to this NLP Crash Course. In 1 hour, we will move from I've heard about NLP to I understand how it works and can start building simple NLP models. Let's start with a quick question. Have you ever chatted with a customer service robot, asked Alexa to play your favorite song, or used Google Translate? If so, then congratulations, you've already employed NLP, or Natural Language Processing. Let me show you some examples in action. Example 1. Chatbot response. When you enter a chatbot and ask, "What's the weather like today?" it reads your sentence, extracts information, and responds, all via NLP. Example 2. Sentiment analysis. Companies track thousands of tweets daily to determine whether people are happy, angry, or confused about their products. That's NLP filtering and classifying words. Example 3. Google Translate. You type "good morning" in English, and voila, it shows up as buenos dias in Spanish. What happens behind the scenes? NLP and machine translation models. So, what are we going to do in this crash course? Here's the goal. By the time this video is complete, you'll understand how NLP is done, the key concepts involved, and how you can start building your own NLP models, even if you're new to the topic. We'll break it down into clear, bite-sized chunks, starting with what NLP is and why it's tricky, then moving into the NLP workflow, the foundations like tokenization and text representation, common NLP tasks, and finally, some advanced topics and modern tools like transformers and Hugging Face. Think of this as a guided tour of the NLP world, with theory, mini demos, and practical tips along the way. And here's the exciting part. This isn't going to be an abstract lecture. You'll see actual code snippets and real examples that make the concept stick. So whether you're a data science student, a developer curious about AI, or just someone who loves understanding how machines understand language, you're in the right place. Let's get started. Now that you've seen a few examples of NLP in action, let's unpack what it is and, more importantly, why it's such a challenging field. What is NLP? Natural Language Processing, or NLP, is an area of artificial intelligence focused on getting computers to process human language. Not just shallow word matching, but meaning, context, and intent. The natural in NLP refers to human languages, like English, Hindi, Spanish, or Mandarin, as opposed to artificial languages like programming languages. At its core, NLP is about bridging the vast gulf between human communication and machine thinking. While human beings speak in sentences, stories, and emotions, machines communicate using numbers and rules. NLP acts as the interpreter between these two spaces, taking natural language and converting it into something that a machine can compute, and vice versa. Wondering where NLP is used? You might not even realize it, but NLP powers a lot of technology we all use daily. Search engines such as Google employ NLP to interpret your query and return the most precise results. Voice assistants such as Alexa, Siri, or Google Assistant translate your spoken commands and carry them out. Language translation software uses NLP to translate text from one language to another without losing meaning. Spam filters for email use content and tone to detect unwanted email. Summarization algorithms condense lengthy news articles into concise summaries. Social networks use sentiment analysis to monitor public opinion through posts and comments. So, why is NLP so difficult? You might wonder, if humans acquire language innately, why can't computers? It's quite simply the unbelievable richness and subtlety of human language. It's not just a question of words. It's a question of meaning, feeling, and context that constantly changes. Ambiguity. Most words carry more than one meaning. Consider the word bank. For instance, it can mean a financial institution, the riverbank, or a bank of switches. While human beings tackle such ambiguities easily with the help of context, machines have to be specially trained to do so. Slang and informal language. Language evolves all the time. Slang words such as "that's lit" or "this movie slaps" can confuse older models. Catching colloquial language, memes, or internet slang requires constant tuning. context, and multiple senses. The phrase, "I saw her duck," has two wildly different interpretations, either the bird or a quick physical action. Good interpretation boils down to extremely subtle contextual clues. Sarcasm and tone. Machines often struggle with tone. "Oh great, another meeting," might be taken positively, but it's actually sarcastic. Sarcasm detection requires more than literal meaning. Structural differences between languages. There are differences in grammatical structures between languages. English's subject-verb-object word order, "I eat apples," differs from Japanese subject-object-verb, "I apples eat." Translation models must contend with these deep synaptic differences. Data quality and variations. Real-world text is messy. It has spelling errors, typos, code switching, use of multiple languages, and variation in writing styles, all of which make consistent understanding a challenge for computers. To gain a better understanding of modern NLP, it's helpful to look at how NLP has evolved over the decades. Era 1. Rule-based systems, 1950s to 1980s. In the early stages, NLP systems were designed using hand-coded rules. A classic example of this is ELIZA, 1960s. A simple chatbot that mimicked a psychotherapist by echoing user input in the form of questions. These systems were easy to manipulate and deterministic, but rigid. They collapsed completely when the input deviated from pre-coded rules. Era 2. Statistical methods, 1990s to 2010s. The introduction of the internet produced a deluge of text data. Researchers began using statistical techniques to learn from data rather than designing specific rules. Models like naive Bayes, logistic regression, and hidden Markov models enabled machines to predict by identifying patterns. These were more flexible, but still struggled to understand long-term context or deeper meaning. Era 3. Neural networks and transformers, 2015 to present. Deep learning revolutionized NLP. RNNs, recurrent neural networks, and LSTMs, long short-term memory networks, improved word sequence comprehension. Later came the advent of the transformer architecture, used in BERT, GPT, and T5 models. That rocketed NLP to unprecedented heights. These models process whole sentences in parallel, learning complex contextual relationships. As a result, today's NLP systems can generate essays, translate languages, summarize text, and more, often with near human fluency. Why this is important to you as a student. Understanding the issues NLP faces helps you appreciate the design decisions that go into the methods and tools you'll study in this course. Each pre-processing step, model architecture, and pipeline component exists to overcome one or more of the aforementioned challenges. So, as you delve deeper into NLP, keep these challenges in mind. Ambiguity, changeable or casual language, context and polysemy, sarcasm and tone identification, cross-linguistic differences in structure, and dirty real-world data. Next, we'll guide you through the NLP workflow, a process of steps that transform raw text into something machine actionable. The foundation you'll gain will leave you ready to build solid NLP applications yourself. Having covered what NLP is and why it's hard, let's examine how NLP projects actually get built. If you took a tour of any NLP team at a tech company, you'd find that whether they're building a chatbot, translation system, or sentiment analysis tool, they're going through a fairly standard process. You can think of this workflow as an assembly line for language. Raw text goes in at one end, an intelligent, task-ready model comes out the other. The exact details vary by project, but the core pipeline usually includes these stages: data collection, pre-processing, feature extraction, representation, model training, evaluation, and deployment. Let's walk through each stage. To make it real, we'll use an example project: spam detection for emails. Starting with data collection. Everything starts with data. Without it, there's nothing for a model to learn from. For spam detection, you'd gather a data set of emails labeled as either spam or not spam. Sources might include open datasets like the Enron email dataset or the Spam Assassin dataset, or internal company data, if available and privacy compliant. Here's the catch. Your model is only going to be as good as your data. If your dataset doesn't contain characteristic spam patterns like "win a free iPhone" or "click here for a special offer," then your model will miss them in the wild. In NLP, more data is better, but representativeness and diversity are just as crucial as size. Moving on to the pre-processing part. Once you have raw text, you can't simply hand it off to a model. Text needs to be cleaned up and standardized so it's easier for machine to deal with. For our example of spam detection, pre-processing might include tokenization, dividing text into words or subwords, i.e., free iPhone today equals free iPhone today. Lowercasing, converting all text to lowercase, so free and free are equivalent. Removing stopwords, tokens like the, is, at, that don't add much meaning in most tasks. Stemming and lemmatization, reducing words to their base forms. Example being running to run. Removing punctuation, numbers, or special characters, task dependent. For spam filtering, this pre-processing step guarantees that free and free are functionally the same signal. Moving forward to feature extraction and representation. Here's the fact. Computers don't really know text. They work with numbers. So the next step is to turn your cleaned words into a numeric representation. Standard techniques include bag of words, BOW, a simple count of how many times each word occurs. TF, IDF, term frequency, inverse document frequency. Scale counts by how often words appear across all documents. This assigns greater importance to unique words like lottery and less common words like the. Word embeddings like word to vec, GloV, represent words in dense vectors that capture semantic relationships. An example being king, man, plus woman, queen. For spam filtering, a BOW or TF-IDF matrix can be sufficient to mark suspicious words like winner, prize, or urgent. Let's proceed to the major component, model training. Now that the text is numerical, we can train a model to identify patterns. For spam filtering, common algorithms are naive Bayes, due to its simplicity, speed, and surprising effectiveness. It remains a popular choice for text classification. Logistic regression, a good starting point for binary classification tasks. Random forests or gradient-boosted trees, good for structured features. Deep learning models like transformers, LSTMs. Excessive machinery for basic spam filtering, but suitable for complex NLP applications. During training, the model will learn to identify which patterns in the features correspond to spam or non-spam labels. Now, let's measure the quality of the model via evaluation. You can't just rely on a model because it works on training data. You must test it on data it hasn't seen yet. For spam filtering, you might use metrics like accuracy, ratio of correct predictions. Precision, out of all emails that we labeled as spam, what percentage were actually spam? Recall, out of all actual spam emails, what percentage did we capture? F1 score, the harmonic mean between precision and recall. If your precision is poor, you're incorrectly flagging legitimate emails as spam, and this irks users. Once you're satisfied with the model's performance, integrate it into your email system so it can start working in real time. When a new email arrives, the model automatically pre-processes the text, extracts relevant features, and classifies it as either spam or not spam. Based on the result, the email is moved to the appropriate folder without manual intervention. But deployment is just the beginning. The model must be regularly supervised to maintain extremely high accuracy. Spam strategies evolve and new patterns develop over time. To maintain the system in operational mode, retrain the model periodically with new real-time data so that it learns and continues to catch unwanted emails efficiently. To conceptually visualize the workflow, consider the spam detection pipeline as a step-by-step process. Raw emails initially undergo pre-processing, removing noise and cleaning text. Next, feature extraction occurs, converting the clean text into numerical features. These chosen features are fed into the model, which is trained and subsequently used for testing. If the test results are acceptable, the model moves on to deployment. Every stage lowers complexity and molds the data into a more helpful format for the model, similar to purifying raw ore into clean metal before constructing a machine. This step-by-step purification guarantees that the model receives the cleanest, most useful input possible. But why is the workflow important? Most newcomers dive right into training models without understanding the pipeline. But this makes debugging incredibly hard. For example, if your model performs poorly, you need to identify the reason. Are the features too uninformative? Is the pre-processing operation inadvertently dropping core words? Or is the training set insufficient or biased? By thinking in terms of a direct, structured process, you can progressively spot and eliminate such flaws and end up with more stable and better performing machine learning models. Remember those challenges we've been discussing? Ambiguity, slang, sarcasm, etc.? Pre-processing normalizes variation in spelling and case. Feature extraction is capable of capturing meaning beyond raw word frequency. Model choice can affect the extent to which context is discerned. The process is not just a series of steps. It's a collection of methods for tackling language complexity. In the second half, we're going to go through it at a slower pace and look at the core foundations: tokenization, stopword removal, stemming, lemmatization, and how you can represent text. We'll also have little code examples so that you can see these steps happen, not just hear about them. Up to this point, we've just glanced at the general NLP process. Let's now spend the next few minutes delving into its foundation, the fundamental building blocks that power nearly every NLP application. This is the equivalent of knowing what ingredients to use before you start preparing a full recipe. Having this background means you can tackle nearly any NLP problem with confidence. In this section, we'll focus on two core areas: text pre-processing and text representation. Text pre-processing covers the steps to clean, normalize, and prepare raw text so it's ready for analysis. Text representation involves transforming the clean text into numerical forms that algorithms can understand. Together, these skills form the backbone of NLP and are critical for building effective, real-world models. When dealing with raw text, whether from social media, emails, or scanned papers, it's typically dirty. Before we feed data to a machine learning algorithm, we must clean and normalize it. This is not just about making it look neat. It's about removing noise, normalizing variation, and making the text machine-readable. The first step to effectively doing this is tokenization, where text is broken down into smaller units, tokens, that may be words, subwords, or characters. Models cannot handle entire sentence as a single string, so breaking it up into tokens gives them manageable bits to work with. Some newer models, like BERT, use subword tokenization to handle unknown words. The provided example code tokenizes a sentence into words with Python's NLTK library and returns them as a list. Lowercasing is another important process that ensures consistency. Without this, dog with capital D and dog with lowercase d would be treated as two distinct tokens. The shared sample code lowers all the tokens in a list to provide consistency. We often also perform stopword removal, eliminating common words like the or is, which typically have little meaning for many tasks, such as classification. For others, such as machine translation, though, removing them would be counterproductive to meaning. The provided example code uses NLTK's built-in list of stopwords to eliminate common words from the token list. And then there are stemming and lemmatization, both of which reduce words to their stems. Stemming uses simple algorithms to strip off word endings, quick but sometimes imperfect. Lemmatization uses vocabulary and grammar rules to find the true root form. Stemming is fine when speed is of the essence, while lemmatization is better when meaning matters. The provided example code demonstrates stemming and lemmatization using NLTK, contrasting the reduction performed by each method. Based on the application, preprocessing can also include stripping punctuation, ignoring numbers, if irrelevant, spell checking, or handling emojis, all of which can be required for sentiment analysis. After the text is cleaned, the second hurdle is that computers cannot read text directly. They can read only numbers. Therefore, we must convert tokens to numbers while holding meaning constant. That is called feature extraction or vectorization. The simplest method is known as bag of words, BOW, which represents a document as the frequency count of words. Basic, but effective for some classification tasks. It doesn't capture word order and results in sparse, high-dimensional vectors. The provided example code uses scikit-learn's count vectorizer to produce word frequency counts per document in a corpus. An extension of this is TF-IDF, term frequency inverse document frequency, where rare, information-rich words get higher weights and common, less informative words are downweighted. This is helpful in tasks like spam filtering, where some extremely rare words are extremely good predictors. The provided example code uses scikit-learn TF-IDF vectorizer to compute word importance scores between documents. But both BOW and TF-IDF do not account for word relationships, like queen is related to king. Word embeddings, word-to-vec, GloV, are where this occurs, mapping words into dense vectors so that semantically close words are close in space. The provided example code trains a small word-to-vec model with Jinsim and retrieves the embedding vector for a sample word. The latest approach is contextual embeddings from BERT and GPT-like models in which a word vector will change based on its context. For example, bank in riverbank is not the same as bank in deposit money. These are contextual embeddings and are likely to give better performance. The provided example code uses Hugging Face transformers to tokenize the input, feed it through BERT, and obtain contextual word embeddings. In an NLP pipeline, an example being for spam filtering, preprocessing guarantees consistency, and representation converts cleaned words into numbers a model can interpret. The decision between BOW, TF-IDF embeddings, or contextual embeddings is based on task complexity and data availability. If your ingredients, your data, are fresh and properly prepared, the resulting dish or model will run much better. Skip or shortchange preprocessing, and even a great model may suffer. With the basics and workflow of natural language processing out of the way, let's jump to the part that gets everybody most excited. What exactly NLP does in practice. This is where theory meets practice, where tokenization, embeddings, and architecture become spam detectors, language translators, or even open-ended question answerers. In this section, we'll explore key categories of NLP tasks, the models that power them, and the trade-offs that determine which approach works best in different situations. Starting with categories of NLP tasks. Although NLP is a broad field, most practical applications fall into three main groups. Text classification tasks, assigning predefined labels or categories to text. For example, spam detection, sentiment analysis, and topic categorization. Sequence-to-sequence tasks, converting one sequence of text into another. For example, machine translation, summarization, and paraphrasing. Information extraction and understanding tasks, pulling out key facts or interpreting meaning. For example, named entity recognition, NER, question answering, and semantic role labeling. We'll move through each category in turn, looking at what makes the task challenging, how it's applied in real-world systems, and which models tend to work best. Now moving on to text classification tasks. We start with sentiment analysis, where the objective is to find whether text expresses positive, negative, or neutral sentiment. Businesses apply it in customer opinion analysis, brand monitoring, and social media monitoring. The challenging aspect? Sarcasm. Oh, great, another day. Can fool simple models, and context matters. Cold could mean temperature or illness. Proven techniques use logistic regression with TF-IDF features, allowing for fast and effective results for small samples. Modern solutions use pre-trained transformers like BERT or distill-BERT, which are more skilled at capturing context and tone. Moving on to spam filtering. Removing unwanted or toxic messages from email inboxes, SMS feeds, or comment streams. Spammers are clever. They constantly modify their text to evade filters, so models must adapt too. Traditional solutions like naive buys are simple, interpretable, and surprisingly effective at simple filtering. Modern approaches like LSTMs or transformers can recognize patterns in colloquial or multilingual spam. Advancing to topic classification, where text is classified into categories like sports, finance, or technology. This happens often in news tagging, customer support ticket routing, or legal document classification. The problem is that topics overlap and there are fuzzy boundaries around categories. The classic approach uses support vector machines, which work well for small datasets. Modern strategies use transformers like RoBERT or Albert, which can disambiguate subtle differences in topics. Now, let's shift our attention to sequence-to-sequence tasks. Starting with machine translation, text translation from one language to another requires more word-by-word substitution. Idiomaticity, syntax, and word order must be maintained. Earlier systems like phrase-based SMT were rule-based and literal. Modern models like T5 and N2M100 excel at idiomatic sense. Open-source tools like Marian MT make high-quality translation accessible. Proceeding to summarization. Summarization can be abstractive, generating new sentences with the same context, or extractive, selecting crucial sentences. Abstractive methods like BERT and Pegasus produce fluid summaries but can hallucinate facts if not fine-tuned well. Extractive models like TextRank need no training but can sound disjointed. Now, let's end the sequence-to-sequence tasks with paraphrase generation, which proves useful for reordering text to avoid plagiarism, simplify wordings, or augmenting training datasets. Conventional sec-to-sec LSTMs can only handle simple rewording, while more recent encoder-decoder transformers like T5 or BERT and generative models like GPT can generate more diverse and human-like rewrites. We also have information extraction and understanding tasks, like named entity recognition, question answering, and semantic role labeling. Starting with named entity recognition, NER, NER identifies entities like people, places, companies, and dates. The tricky part is handling vagueness. Is Apple a business or a fruit? Early CRF-based models relied on handcrafted features, but transformer-based NER models like BERT NER handle context much better nowadays. For question answering, QA models, they either identify the answer from a given context, extractive QA, or generate the answer via generative QA. BERT performs well in extractive setups, like the SQUAD benchmark, while T5 and GPT models are used to support open domain conversational Q&A. Finally, semantic role labeling labels sentence constituents with roles basically identifying who did what to whom. This is useful for information extraction, legal document analysis, and chatbot intent detection. BIL STM CRF systems were once traditional and adequate for well-organized text. Transformers now dominate for nuanced, long-range dependencies. Lastly, we have cross-cutting and emerging tasks, fields of NP that cut across conventional category boundaries. Speech-to-text and text-to-speech power voice assistants and transcription engines, with prominent models including Whisper, Deep Speech, and Tacotron. Multimodal NLP combines text with imagery, video, or audio, opening up capabilities into image captioning with CLIP and GPT. Dialogue systems have moved from rudimentary rule-based scripts to sophisticated conversational models such as ChatGPT or Llama, which have the ability to store long-term context and dynamically adjust responses. These applications reflect the growing range of NLP and create a juxtaposition with older, specialized versus newer, generalized models. Each presents unique strengths and trade-offs, impacting performance, flexibility, and the capability to deal with intricate, real-world situations. For sentiment analysis, older techniques such as logistic regression using TF-IDF are quick and effective, but newer ones like BERT and distill-BERT perform well on context, sarcasm, and subtlety. Naive Bayes spam classifiers are interpretable and adequate for simpler scenarios, while LSTMs and transformer-based models accommodate changing multilingual spam. SVMs are good with small-sized data for topic classification, but transformers such as Roberta and Albert work better on sophisticated, uncertain topics. Machine translation has progressed from rule-based plain language SMT to models such as T5 and MTM 100 that handles idioms, low-resource languages, and grammar with better fluency. For summarization, TextRank is zero-shot but tends to give stiff output, while BART and Pegasus generate natural and short summaries with some possibility of hallucination. Paraphrase generation has transitioned from SEC to SEC LSTMs to transformer models such as T5 and GPT, providing varied and style-controlled paraphrasing. For named entity recognition, CRFs use hand-engineered features, whereas BERT NER can easily transfer across domains. Question answering progressed from BDEF to BERT and T5, from extractive to generative tasks. Semantic role labeling developed by Belstem CRF to transformer encoders for long-distance relationships. Dialogue systems moved from rule-based scripts to LLMs such as GPT, Llama, and ChatGLM. Dynamic but necessitating safety precautions. Generally, traditional models are appropriate for lightweight and interpretable tasks. Transformers hold sway over complicated and subtle applications. Selecting the optimal NLP model depends on several key factors. First, consider the availability of data. Large transformer models thrive on massive datasets, while smaller models often perform better with limited data. Next, think about your computational budget. Fine-tuning large GPT-style models can be costly and resource-intensive, whereas lightweight models like distill-BERT are much more affordable to train and deploy. Lastly, the complexity of your task matters. Simple tasks such as keyword filtering might not require deep learning, but nuanced tasks that need contextual understanding usually do. Today, the NLP landscape is incredibly accessible. Thanks to platforms like Hugging Face, pre-trained models can be fine-tuned even on a laptop, enabling small teams to build powerful applications. By grasping each task's nature, its challenges, and the models it's suited for, you can confidently select the right approach, whether that's detecting misinformation, translating multiple languages, or creating chatbots capable of engaging conversations. The past decade has seen a paradigm shift in natural language processing, from sequential models to reasoning architectures capable of managing enormous amounts of data with uncharted efficiency. Before 2017, RNNs, LSTMs, and CNN-based models pervaded the scene, offering high performance on sequence modeling but terrible management of long-range dependencies and sequential, time-consuming computation. A breakthrough came with the transformer, first introduced in Attention is All You Need. By removing recurrence and solely relying on self-attention, transformers enabled parallel processing of sequences and cross-distance word relationships, allowing a model to link dog with was fast even across numerous clauses. Scalable to billions of parameters, this architecture became the foundation of modern NLP. The invention of transformers transformed NLP by making it possible to develop high-capacity, pre-trained language models, PLMs. Rather than creating task-specific architectures, scientists started training large models like BERT, GPT, T5, and BART on huge text corpora and fine-tuning them for their target tasks. This brought tremendous gains in efficiency. One model could process a variety of tasks like sentiment analysis, summarization, translation, and question answering with little task-specific data. With increasing computational power and dataset sizes, newer models such as Palm, Llama, GPT-4, and Gemini were born that extended these boundaries of scale and capability. These newer successors proved that a single general-purpose model could easily tackle nearly any NLP task, saving development time while achieving better performance. This paradigm change not only optimized the NLP process, but also gave a massive boost to artificial intelligence applications, allowing superior language understanding and generation to become ubiquitous across many industries and research fields. While transformers transformed NLP, the initial full self-attention mechanism had high computational costs for extremely long sequences since it completely grew quadratically with sequence length. This bottleneck led to advancements in attention mechanisms to make them more efficient. Sparse attention models such as Longformer and BERT minimized computation by focusing only on a subset of tokens, making processing long contexts practically possible. Linear attention techniques further enhance scalability to O of n complexity, enabling the processing of sequences with thousands of tokens. Hierarchical attention enabled a multi-step mechanism that divided documents into manageable pieces, encoded them independently, and subsequently pooled the representations. All these advancements cumulatively extended the transformer's scope and enabled processing of entire books, long legal agreements, and multi-page meeting minutes, without running out of computational resources. By resolving the full self-attention bottleneck, scientists opened up fresh avenues for using transformers in fields that need deep context understanding across long stretches of text. In parallel with such architectural developments, the interaction between human users and large language models has changed with the progression of prompt engineering and in-context learning. Rather than retraining or fine-tuning a model for each new task, users can now guide its behavior by writing natural language prompts. Methods like zero-shot prompting enable a model to accomplish a task without examples, and few-shot prompting provides a few demonstrations to enhance accuracy. Chain-of-thought prompting extends further, compelling the model to think step by step for more difficult problems. This change reduces the entry barrier, enabling both technical and non-technical users to program the model by simply framing requests well, without changing its innate parameters. The outcome is an easy-to-use and more versatile AI process, in which anyone from developers and researchers to educators and business analysts can reconfigure a single strong model to fit many different uses with nothing more than thoughtful prompts. Current NLP has moved beyond the processing of pure text to incorporate multimodal abilities, combining data from images, speech, and video when processing with language. Models such as CLIP connect text and images, which allow for applications such as zero-shot image classification and searching for images. Flamingo builds on this by processing mixed sequences of text and images for tasks such as visual question answering. Whisper focuses on speech recognition and transcription, while models such as Video Llama venture into video understanding that pairs temporal and visual signals with textual reasoning. Such improvements allow for a broad range of applications, from generating image captions and answering questions about diagrams to enabling voice-controlled assistants capable of further interpreting visual context. By reasoning and processing multiple modalities, such models move closer to human-like perception, where comprehension is no longer limited to words but augmented by vision, hearing, and temporal context, opening up more engaging and intuitive AI interactions. To enhance factual accuracy and relevance, most contemporary NLP systems utilize Retrieval-Augmented Generation, RAG. Here, a language model is combined with a retrieval module that searches external knowledge bases or the web in real time. Documents retrieved allow the model to write responses that are current and domain-specific. This is especially useful for fast-changing domains such as news, law, and scientific experiments, where fixed training data rapidly becomes stale, meaning model adaptation has been made faster by parameter-efficient fine-tuning methods like LoRa, prefix tuning, and adapters. This updates a tiny portion of model parameters, with a huge reduction in computational and storage costs while maintaining excellent performance. This allows organizations to tune larger models to specialized domains, such as healthcare, finance, or legal work, Without the expense of complete retraining, bringing advanced AI capabilities more within reach and at scale for everyday use. What about higher level generation? In contemporary NLP, complex text generation methods improve the quality and flexibility of model outputs. Beam search tries out numerous potential continuations at every step, choosing the most coherent overall sequence, so it works well for tasks such as translation and summarization. Top K sampling adds diversity by limiting options to the K most likely tokens, while Top B, nucleus, sampling chooses the smallest subset of tokens whose combined probability is above a threshold, trading off coherence with creativity. In addition to sampling, RL-HF, reinforcement learning with human feedback, brings models into better alignment with user intent and human values by adding human preferences to the optimization loop. These methodologies make it possible for models to generate contextually suitable, interesting, and pertinent outputs in a range of applications. Collectively, they enable text generators to respond more effectively to subtle demands, whether maintaining factual accuracy in technical documentation or encouraging creative voice in narrative writing. The next level of NLP development is dominated by a push towards models with massively wide context windows, so that they can process and reason over entire books, multi-day conversations, or huge knowledge graphs without losing track of low-level details. Simultaneously with this, richer multilinguality is emerging, in which models can read and write dozens of languages effortlessly, bridging cultural and linguistic divides. Personalization innovations means assistants will learn how to adapt along the way and acquire user preferences, communication habits, and task domain needs, giving rise to more natural and context-aware interactions. Such capabilities signal an evolutionary shift from reactive tools towards proactive assistant partners that can assist in very specialized, long-duration workflows involving research, creative work, or everyday tasks. This trajectory shows NLP's future lies far beyond text manipulation. It's moving towards intensely multimodal reasoning that integrates text, vision, speech, and even motion. These systems won't just respond to commands, but understand rich, real-world contexts and anticipate user needs, enabling richer and more natural collaboration. Imagine assistants that are able to read a report, look over related images, understand spoken explanations, and then act, like generating a presentation or controlling devices within one unified process. This confluence of modalities brings AI closer to human perception and intellect, but with machine intelligence accuracy and scalability. As these capabilities mature, NLP will be the backbone of intelligent systems that dialogue transparently across the many human communication paths, transforming the way humans work, learn, and innovate. We've covered a lot of ground in this crash course, from what NLP is and why it's tricky to its building blocks, methodologies, real-world applications, and finishing up with bleeding-edge trends. Throughout it all is the intersection of linguistics, computer science, and machine learning, making machines read, comprehend, and produce human language. The challenge is in the intricacy of language, idioms, vagueness, cultural context, and the difference between stating something and what is intended. Examining the roots, we were able to understand how text representation, like bag of words, TF-IDF, and embeddings, morphology and syntax like tokenization, POS tagging and parsing, semantics, i.e., word and sentence meaning, and pragmatics discourse via context interpretation from a process stacking upon one another. Together, these building blocks transform raw, unstructured text into structured meaning, which can be read by algorithms and acted upon. NLP takes us from raw text to useful output in a linear series of steps. It starts with text gathering, pulling data from documents, websites, or speech inputs. Then comes preprocessing, which involves cleaning and normalizing the text, tokenizing it, and dealing with out-of-vocabulary words. Feature extraction follows by transforming the text to numerical vectors that are comprehensible to models. During the model training stage, Machine or deep learning models are trained to execute a concrete task. Performance is measured by metrics such as accuracy, F1, BLEU, or ROGUE. Last but not least, deployment positions the model into working systems, with continuous surveillance for performance drift detection. This template addresses all NLP applications, from spam filtering and sentiment analysis through translation and question answering, bridging theory with real-world, effective AI solutions. We also discussed the primary NLP model categories: rule-based systems, statistical models, and the age of deep learning using RNNs, LSTMs, GRUs, and transformers. Each had its own strengths and compromises. And the coming of pre-trained models such as BERT and GPT revolutionized the field by making powerful general-purpose language understanding possible. In our concluding segment, we looked at cutting-edge topics: transformers and large language models, prompt engineering for zero and few-shot learning, multimodal and multilingual systems, ethical factors like bias, fairness, and explainability, and low-resource NLP for assisting under-resourced languages. This indicated that NLP's frontier is as much defined by responsible, inclusive innovation as by sheer ability. The major takeaway is that NLP is as much art as science, demanding excellence in algorithms, ingenuity in dealing with noisy data, and a linguist's instinct to craft solutions that are effective in the messiness of real language.